Hey everyone! This series of videos is going to walk you through pages 34 to 36 in your packet, which represents a summary of Riemann sums and how we end up seeing them in context when it comes to calculus questions. In the first section up at the top of page 34, it may be worth it to pause this video and read the tying it all together comments, just so you can give yourself a bit more context for what exactly we're doing and why we're doing it. In essence, to summarize, the real life significance of an area under a curve can actually have some pretty far-reaching implications. Just kind of like when we saw problems with rates of change or slope, we saw all sorts of real life connections. For example, when we learned derivatives, we realized that derivatives were linked to things like velocity and acceleration, which has lots of application in the physics world. And just as we learned that slope or derivative represented rates of change when it comes to those real life scenarios, area has real world connections as well. It's not that you're literally finding the area of real life objects. That's kind of a geometric application. But when we say area in this context, the representation, what the area represents, is actually the part that has some real life relevance. So once we do the first example, I think you'll start to see how this actually does fit in a real world context, and why the area isn't actually to be taken as literally as you might think. Now, on this page, we're going to tackle the example in question number 6. And once we do that example, you'll be well equipped to do many of the questions on pages 35 and 36. This playlist is essentially going to walk you through page 34 and one of the examples on page 35, with the goal that you can use these examples to work independently on the remaining questions. That said, let's spend some time together in this video making some sense of this example, because this example is very indicative of the type of skill set that you'll need to apply in the remaining problems. In this example, we're dealing with a car coming to a stop 5 seconds after the driver slams on the brakes. While the brakes are on, the velocities are recorded in the table over here, and we want to determine the total distance that the car took to stop. So naturally, you can probably think about this connection that we already know between distance, which is kind of a position, and velocity, its derivative. We know that those things are related. So in letter A, we can definitely kind of keep that relationship in mind when it comes to fleshing out an answer here. If the data in the table is velocity data, then it stands to reason that the velocities that we see here must be derivatives, or rates of change, or slope, however you want to phrase that, of the distance at each second in time. Now, that doesn't really make as much sense. You hear it and you're like, wait, derivative of distance. So you might want to think about the word position as a more familiar word or synonym for distance, because technically position and distance are kind of the same thing in this context specifically. So we can infer that if the derivative of position is velocity, then the antiderivative of velocity must be position. So this data in the table is essentially a set of derivatives. And if we want to work backwards to figure out distances, we must have to take some antiderivatives. I do suggest, just so you can kind of chew on this idea a little bit, that you pause the video, take some time to let that idea sink in, and take some time to put your answer for letter A in your own words here, because while I'm not going to write out a sentence for you to copy, I do think the essential idea is important and definitely worth thinking about a little bit before we begin the actual mathematics. So if you need to take this opportunity to pause the video and put things in your own words, this would be a great time to do so before we start building on that idea any further. Once you're ready to move on, we're going to take a look at question letter B, where we want to acknowledge that if velocity requires an antiderivative to get to position, we naturally would just think, well, take an algebraic antiderivative, use the power rule or something. But if you notice, there's no equation given to us. So an algebraic antiderivative isn't possible because I don't have an equation to work with. I don't have an equation for which I can see a power rule or a known derivative. So this is where we're going to have to think conceptually about the synonymous relationship between antiderivative, which is a word we know we're very familiar with now, and area. Area is now synonymous with antiderivative. Remember just how slope and derivative are synonymous with each other? Area and antiderivative are also synonymous. So in letter C, instead of taking a traditional antiderivative algebraically, the best we can do is find the area under this velocity curve, because that is, as we found with Riemann sums, essentially an estimate of the actual value of the algebraic antiderivative. So I'm going to phrase this specifically, and you're welcome to copy down this phrasing. We're going to find the area under the velocity curve. Now, to do that, we're going to need a visual, because area is implied to be a geometric or a spatial relationship, and I do want to make sure that we have some way of doing this visually with the geometry skills that we already have. So in question letter D, we're going to plot this data and create a velocity curve for ourselves. Since we don't have velocity equations to work with, the velocity curve is going to have to simply come from these points. So in letter D, where it says plot the given data, we're just going to do the best we can to kind of plot the points as reasonably as we can without any sort of tick marks or guidelines. The x-axis here is going to be our time, because the x-axis is always our independent variable. And I'm also going to label the units, because it does say label your axes with what they represent and with appropriate units, so we definitely want to heed that direction. So the y-axis then must be the velocity axis, and its units are feet per second. Those units are going to come in handy in a moment, and you'll see why. Now, as plotting the dots goes, we probably will want to just kind of estimate the best we can using a scale that is reasonable. I don't want to make a whole lot of tick marks and stuff, because that just tends to get really tedious and really annoying. So I'm just going to plot what I need. Now, in terms of the x coordinates, it only goes up to time 5. And you can label each individual coordinate if you want to. It's kind of up to you. The y coordinates don't seem to have any sort of nice relationship, so I'm going to kind of cheat a little bit, which is totally allowed at this level, because let's be honest, this is a calculus class. We're not in it to really dictate, like, oh my gosh, do you know how to make a graph? You proved that to us many, many times in all of your previous classes. So we're just going to make a quick and easy graph, because area right now is the bigger priority. 0.88, I'm just going to kind of assume, is somewhere on the y-axis, somewhere up there. I'm just going to make kind of a random dot, and I'm going to call that 88. I'm not going to individually mark each individual tick mark. I'm not going to say, ooh, I'm counting by 10s or I'm counting by 5s. I know mathematically that's probably the right thing to do, but right now it is not important, and you'll see why once we get the rest of this problem going. So let's just quickly plot the rest of these points with an equally casual attitude. 1, 60. I don't know, I'm just estimating, maybe like right around here. And 2, 40. I don't know, somewhere right around here. You'll see that I'm taking a lot of liberties with this, and I'm just labeling the coordinates instead of painstakingly creating all these little tick marks. 3, 25, again estimating. 4, 10, again estimating. And 5, 0, thank heavens that one can be accurate. So we're good to go. Now, if you notice this velocity curve, it's definitely not really like an actual recognizable shape. I mean, it's definitely not a linear relationship. You can see that the distances between the lines vertically are not consistent. And we can probably infer, although probably not reasonably certainly, that they are continuous in nature. Because if you think about the situation, you've got a car coming to a stop. The car is going to travel for this entire interval along a continuous timeline. It is possible that the car could stop after 0.5 seconds and we can take a measurement, or 1.3 seconds and we can take another measurement. So it is reasonable to infer that the curve is probably continuous, even though they didn't give us this data. So you may just want to assume a connection. If you want to draw a connection, that's fine, just to give yourself that visual. But we can't infer anything about an equation or anything more specific, so let's not go too far with this. Now that I have my plot, in question letter E it says, find the approximate distance the car took to stop using a left Riemann sum. That phrase is actually going to be kind of important to us, because that's going to dictate how we're going to find these areas, how we're going to set up these areas. A left Riemann sum means that each rectangle that I want to draw on the graph needs to touch this curve or touch the data points in their left-hand corners. So to create a left Riemann sum, here's the easiest thing. Start the furthest you can on the left, so that would be this dot here at 88, and draw the horizontal, or what will be the top of your rectangle first. So notice I purposely drew the top of my rectangle so that its left-hand corner is this dot at 88. Then, once you've reached where it looks like that rectangle would cut off and the next rectangle would start, just drop the height straight down. If you want to be really particular and use a ruler, this is probably a good time to do so. I will freely admit I will be a little less type A in this video, so if I make some truly horrendous lines, please don't judge me. Now I'm going to repeat that process for the rest of these data points. So 60 needs to be the left-hand corner of my second rectangle. And notice I'm just extending it far enough to the right that it would represent like one full distance or one full tick mark, and then I'm kind of stopping. So notice I stopped right above where the next dot looks like it would begin, and then drop the height straight down. Same thing for 40. I'll extend across and then down. 25 across and then down. 10 across and then down. And notice this data point at 0 is interesting for two reasons. First, because I actually can't use it as a left-hand corner. If I extend any rectangles past this, I'd be outside of my interval, which I don't want, and it's at 0. So even if I tried to make a rectangle here, it wouldn't have any height to it. So that one, fortunately, kind of worked out pretty well. Now that we have our rectangles, we can make a couple of inferences. First, we can definitely tell that this rectangular area is going to be an over approximation of the actual distance that they're asking about in the question. Because if we think about each of these areas, both individually and as a sum, we're going to be finding these little extra pieces that pop up above our presumed velocity curve that we know we don't want. We can't help it. That's the downside of using rectangles, as we discussed in the previous playlist. So we just kind of have to deal with that. Now, of course, we're going to find the areas just to get that part done. And then we'll figure out what's going on with the sum. Each rectangle has an area of base times height. So if we just do each one individually here, we can tell that the first rectangle has a base of 1 and a height of 88 for a total area of 88. The second rectangle has a base of 1 and a height of 60. The third rectangle has a base of 1, height of 40. So these calculations are practically trivial because we're not actually calculating. 1 times the y-coordinate is just going to be the y-coordinate. We just have to make sure that we're kind of organizing ourselves. So this last rectangle is 1 times 10, and now we have all of our values. If we find the sum, or the total of all of those values, each individual rectangle added up, we should get a total of 223. So if you want to double check your answer and just make sure that you also got 223, that should represent the value of our supposed area. Now, if you think about this in context, there are a couple of things that I want to make sure that we connect. First, the approximate distance the car took to stop is what we're using the left Riemann sum to find. And if you're looking at that number thinking, that's a distance number, perhaps some units will come in handy. What I'd like to take the opportunity to do right now is to actually look really closely at one of these rectangles so that you can see why it actually is connected to distance. That connection probably seems really strange, so bear with me for a second. I'm just going to recreate one of the rectangles. Specifically, I'll just recreate this first one from 0 to 1. Now the x-axis was measuring from time 0 to time 1, which means if these were our time values, the x-axis is measuring in seconds. So the gap from 0 to 1 is a number of seconds that I was traveling. The y values were velocities, which means when I was finding the height from 0 to 88, that represented an 88 feet per second velocity, which I'll just make a mention of. Its units are feet per second. So when I found the area, I did base times height, which is the number of seconds times the number of feet per second. And if you think logically, when we did base times height, so I just want to make sure that we can see what we're doing here. When we did base times height, think about what happens to these units. The base number was in seconds, so for example, 1 second, times the height number was in feet per second, 88 feet per second. And notice what happens when we do that multiplication. It's almost going to harken back to, for those of you who did chem either recently or in the distant past, it's almost going to kind of harken back to that dimensional analysis or stoichiometry kind of idea, where you're looking at what's happening to the units almost as if they were happening mathematically. 1 times 88 is going to multiply, but secant, same abbreviation, seconds on the top and seconds on the bottom of this calculation or this fraction are going to cancel each other out. So when I multiply 1 times 88 and I get an answer of 88 or an area of 88, the units with 88 are feet. And when we actually think about that in context, 88 feet is a distance. That must be how far I traveled in this first second of my ride. So if I kept traveling for every single second from 0 to 5, this area represents how far I went. And that is the interesting thing about the connection to area, that when you actually look at all of these individual rectangles, they're not just rectangles. Each of their individual areas represents how far the car went in that increment of time. So we can assume, and this is mathematically why the units work out the way they do, that in the first second, from time 0 to time 1, we traveled 88 feet. I'll put a little foot tick mark there, just for reference. In the next second, from time 1 to time 2, we traveled 60 feet. In the next increment, from time 2 to time 3, we traveled 40 feet. Now, it does kind of make sense that these numbers are getting smaller because the car's slowing down. As I move more slowly, the car is going to cover less ground in each second that it's traveling. So it actually does make sense that I'm seeing this sort of decreasing effect. Between time 3 and time 4, I'll travel 25 feet. Between time 4 and time 5, I'll travel only 10 feet because by now my car is going quite slowly. So in total, I must have traveled 223 feet. And when you actually think about it, it's almost uncanny that by simply finding a regular old area, we're actually doing something that sounds practically like a physics problem. We're figuring out how far we went, and all we knew was how fast we were going. So that, to me, is the most fascinating connection between these antiderivatives, which from a calculus standpoint aren't really that interesting, and the areas that they represent. Because the area that they represent isn't just a visual way of doing an antiderivative, it actually means something in context. The area really is the distance that we traveled. So in question letter E, when we say that our answer is 223, let's make sure that we include 223 feet for relevant units. because that's really what this answer represents. It represents how far we traveled from the time that we applied the brakes to 5 seconds later when we stopped measuring. Now in question letter F, it's going to ask you to do the exact same set of points, but with a trapezoidal sum instead. So this is where I'm actually going to ask you to try this on your own a little bit to practice your technique for not only creating trapezoids, but for actually finding the areas. You'll recall from the previous playlist that finding trapezoids is a little bit more nuanced. So I'll just quickly draw a trapezoid here just to make sure that you have the right idea, and then refresh your memory a little bit on what's going on. To find a trapezoidal area, the first thing that you'll want to do is partition your graph into its individual trapezoids. I like to do one at a time. I also like to color code them, but it does help to have some sort of visual approach. Now, the other thing that I like to do, just as a reminder, is to rotate my trapezoids so that I can see the bases, base 1 and base 2 respectively, and the height a bit more clearly. So for this trapezoid, for instance, just to make sure that we have something to work with, the formula is going to be 1/2 base 1 plus base 2 times height. So base 1, if I rotated it this way, is going to be 60, plus base 2, looks like it's going to be 88, times the height, which is going to be 1. So I'll quickly do that calculation. 60 plus 88 is going to be 148, and half of 148 is going to be 74. So that gives me the area of my first trapezoid. And just like before, you might want to make some sort of labeled list of numbers for yourself or something, just so you can keep each individual area straight. Once you've found the area of each individual trapezoid, you'll be adding them up. So again, just for ease of visualization, you might want to consider color coding or breaking up your trapezoids into smaller pieces and doing them one by one so you can more clearly see them. You can probably infer that the answer that you're going to get for your trapezoidal sum will be significantly different and perhaps less than the answer that you got for the rectangular or Riemann sum, because there's less wasted space with trapezoids. Notice that your trapezoid more perfectly approximates the actual curvature of your velocity and doesn't have that waste effect. So by the time you get all of your trapezoids drawn, and just as a funny little technicality, this last shape really isn't a trapezoid. This last shape is actually a bit of a triangle, but you can call it a trapezoid where base 1 is 10 and base 2 is 0. It actually works the same. Fun geometric fact. In any case, this is where this video is going to end. So between now at the end of this video and the beginning of the next one, I'm going to encourage you to try question letter F, which is the approximate distance using a trapezoid, and then in question letter G to put some of these contextual thoughts into words to really make sure that you understand why the units work the way they do. As an additional challenge, try to think about the units for a trapezoid and prove to yourself, using that kind of stoichiometry approach that I used on my scratch paper here, to help you understand why even with trapezoids, the units still come out to be feet. So, spoiler, your answer to letter F is also going to have feet as your answer units. So if you can, try to kind of derive where the feet come from, and that should help when it comes to understanding why no matter what kind of area you do, rectangular or trapezoidal, it still ends up representing the feet or the distance that you travel.